We're happy to have Denis to give us the encore talk about Gromov-Witten and
Hurwitz wall crossing.
So,
yeah, thank you for coming so early. Witten. Yeah, so the title is Gromov-Witten Hurwitz wall crossing, and it's not quasi-maps, so it's something else, but it's related to quasi-maps. And so what is the upshot here, essentially? So upshot is the following. So with quasi-maps, we got this wall crossing between Gromov-Witten theory of, let's say, Hilbert scheme of endpoints and Donaldson-Thomas theory of that surface times this curve. But there exists a similar kind of a wall crossing where you consider, instead of Hilbert schemes, you consider the symmetric product of S. And the wall crossing between, the theory that you wall cross to is one might guess, is the Gromov-Witten theory of S and C. So by symmetric product, I'll always mean the orbifold symmetric product. So I take the n copies of our surface and the quotient by the symmetric group, and I take the orbifold, not the coarse. And so this is what I call Gromov-Witten Hurwitz wall crossing. I'll explain why Hurwitz appears in the name. I mean, in the terminology. And so what it gives us, so this kind of wall crossing and quasi-map wall crossing, these two guys together give us essentially an equivalent of a so-called Kreppin resolution conjecture. And on this side you have DT Gromov-Witten correspondence. Well, at least relative one, so with the relative insertions. And so, so you.
So the left hand side is the same, like the GWC. Right?
Say again? The right hand side?
No, left hand side.
The brackets again.
Sorry, yeah, I'll always. This is a curly bracket always.
Okay.
So that will be an issue for the entire talk.
Yeah, exactly.
Yeah, so I'll make sure to make it like. This is just a symmetric orbifold. This is Hilbert scheme.
It's singular. Okay, it's singular.
Yeah, so in some sense, the Hilbert scheme and the symmetric.
Okay.
So they sit over the coarse symmetric the coarse symmetric product, and two of them. I mean, the Kreppin resolution refers to the fact that when you take the symmetric orbifold, you take its coarse. It's the coarse space. It's a singular space. You resolve it, and the resolution is Kreppin and isomorphic to the Hilbert scheme. And the Kreppin resolution conjecture states that essentially the Gromov-Witten. I mean, I will state in the end what it means precisely, but roughly speaking, it means that if you take Gromov-Witten invariance over here on a Hilbert scheme side, you analytically extend the generating series, and you then specialize at some point -1, and you get the invariance on the right hand side. Yeah. So I'll it will be. I thought about it, but I didn't know how to. I mean, okay. What I can do, I can put always the brackets to indicate that's a stack. Yeah.
I think isn't this better to write like C N or F?
Yeah. That's well. It's also if you write this as a Hilbert.
Yeah.
That is true, but it's somehow.
Yeah, but then it just takes lots of time.
Everything is denoted by S, and then it's either up or lower in symmetrical results, and then. Yeah, that's the point.
Yeah.
the same letter, then it's
Symmetric product will not. I mean, symmetric group will not appear that often.
Okay.
That's why.
Which is why in my notes I didn't use recommendation.
Well, okay, I can. Yeah, okay.
No, that's fine. That's fine.
Yeah, I'll put the brackets.
This is good. This is good. Kind of keep us on like pay attention.
So I'll always put the brackets in order to make it clear.
We should also we can like add like tones.
like in Chinese.
Nice. Okay.
So what was the previous result about this Berkeley resolution?
What?
What was the previous result or some previous result?
Yeah, sure. I mean, it's, okay. I will come to Kerpen resolution conjecture in the end. This is just an upshot. I mean, that's just an introduction. I mean, I haven't even specified what is Kerpen resolution conjecture. But what I want to show, I want to say is that I will denote Kerpen resolution conjecture by CRC. Okay. Kerpen resolution conjecture. So essentially, these two wall crossings give you that the Kerpen resolution conjecture is equivalent to this Gromov-Witten correspondence. DT Gromov-Witten correspondence. Yeah, no. In this case, for C times S times C. Yeah, so for S times C, I mean, which is also kind of fundamental, right? Because yes. So what did I want to say? I guess that's it.
So you're saying your achievement is like proof two horizontal rows to translate them.
Yeah, exactly. Well, I'm not claiming here that CRC Kerpen resolution conjecture is more. I mean, I'm not claiming that this actually allows you to prove, let's say, DT Gromov-Witten actually for S times C, because DT Gromov-Witten for S times C is computationally simpler than CRC, but CRC is more geometric, so you still can. I mean, it depends on what is your goal. So actually, with that, I can prove some CRC, and for certain, I mean, for Delpetis, for example. But because DT Gromov-Witten is easier. But at the same time, CRC is more geometric, so you can get from CRC you can get this. You don't need the variable substitution, so you get it for free. There you just need the specialization. You need the analytic continuation. I will talk about it.
Is really analytic continuation or just a rational function?
Well, I guess well, on this side it's not a rational. Okay, on this side it's, I guess it will be a rational function at most. So by analytic continuation, I mean, extending it, generating series to some.
Something is rational function.
Yeah, and then specializing it -1. Okay. So okay, let me just. So for that I need to recall, I mean, what is this? Yeah, let me write then, it's true that it's probably going to be complicated. So I'll write this to be sim of S. Does it look good? So, okay. So first I have to actually tell you what I mean. What is actually the Gromov-Witten theory to the orbifold, right? So if you take a map to sim of S. So this map.
Actually, is a quantity.
In what sense?
There's like a CMS is the quotient by a group.
Yeah, but you don't have the unstable locus. Yeah. So, but what is this given by? So I'm claiming that it's not difficult to check that this data. So, but just by the fact that CMS is a quotient of something by group. So what is a map from a curve to CMS? It's a Cn bundle over C with an equivalent map, right? So it's some, I'll call it. So this is Cn bundle with a Cn equivalent map to Sn n-fold product of S. But that you can also show that this data is actually equivalent just to degree n cover and of no ramification. When I say cover, no, so there are no ramifications. And with a map from that cover to S. Okay. So a map from C to the symmetric product is the same as Sn bundle over that C with this Sn equivalent map to n-fold product of our surface. But this is also equivalent to the data of degree n cover without ramifications to our C with a map to S. Okay. So what are insertions in this theory? So because we have an orbifold, well, when we take a curve with a marked point, if this curve is just a scheme, if it's a variety, right, then you don't see the orbifold structure. So you have to fix it somehow, and so you introduce this twisted curves. So the twisted curve is just a curve whose marking is allowed to be allowed to carry some stabilizers of finite degree. So when I write that, I mean that P is locally isomorphic to the quotient. C at P is locally isomorphic to the quotient of C by BZM, where you act by roots of unity on C. So in this case, when you evaluate your point, so you don't map to the symmetric product itself, but you actually map to the inertia stack. So what is inertia stack? Inertia stack is just defined to be maps from this finite abelian gerbs to the symmetrical. So where you vary m as well, you take arbitrary m. In this case, it also can be shown that the inertia stack can be actually expressed as a disjoint union over partitions of n such that your quotient, so you take the product self product of S over partition viewed as a finite set, and so you then quotient down by automorphisms of that partition. Well, it's equal up to some rigidification. There's some. Okay, and so what does it say? So when you introduce this kind of twisted orbifold structure, this is a. Yeah, it's. Yeah. So it's automorphisms of. I mean, here you require it to be representable. I mean, M is the order of stabilizers of the point the points.
So you have some orbifold point in your domain curve.
Yeah, exactly. Yeah, so so your curve now has this. So it has the marking, but the marking has this little gadget now, which is just a ZM, so ZM stabilizer. So it just looks locally. It looks like that. Sorry, I meant quotient by ZM. So you see at the origin you have ZM stabilizers.
The requirement is that the map of stabilizer is injected.
Yeah, exactly. So it's representable. Yeah, very. Yeah. So what I want to say, you can express this in the same way now. So you can express the data of this twisted curve mapping to the symmetric product in the same way as we did it there. So this can be actually shown to be equivalent to now a cover from C prime, some other curve, to C with a map to S, such that it's still a cover, but with a ramification at the point P. Okay. So cover of degree n. So the data, just to emphasize, the data from a twisted marked curve to the orbifold symmetric product is equivalent to the data of degree n cover with ramification at this point P. But ramification, in this sense, it becomes some kind of insertion. So insertions in this theory, essentially, it's ramifications with a of type, let's say, mu with a length mu classes in S. So each ramified point in C prime gives you a marking, and you just pull back with that marking classes from S. So if S, for example, was a point, so S, let's say, I mean, this for us S is a surface, but actually what I'm saying holds for any variety, and in particular if S is a point. So this, everything that I just said would imply that the data of curve to the to B Sn, so the classifying space of a symmetric product or symmetric group, is just equivalent to covers of C, and the insertions will be just a specification of ramifications at the markings of these covers. And
so just to make sure the inertia stack, the unions over with mu or something.
Yeah, mu.
Mu dividing n.
Mu, it's partitions of n.
Oh.
Partitions.
I'm a little bit uncertain. So there's m for every point. So
Yeah.
This little m to this ramification. Is there some restriction on the ramification depending on m?
Yeah, so it's not directly related to the data of a partition. Okay, I mean, so I wrote down rigidification here, but honestly, so when you do that, you take conjugacy classes of your symmetric product. You take the fixed loci and you quotient down by the centralizer of G, and so this M will be related to the order of this centralizer acting on a fixed point. So M, you vary M here. You take all different M's and. Okay, give me a simple example. I mean, if you take just a simple.
You can imagine M is infinity, then you take all partitions.
Yeah, but I'm taking all m's here. I mean, you mean you're taking
some
z.
divisibility between, I think, the products of mu and some stuff.
Yeah, sure, I mean, okay.
So can I understand this? Like you have some stratification of your sim M
Yeah.
according to how many points cluster together, and how points cluster together, and then
Yes.
disjoint union is the disjoint union over the clustering time partition.
Yeah. So you
What is the auto mu? Sorry.
automorphisms of a partition. So if you have a partition here, and if you have repeated parts of this partition, then you act by the symmetric product of it.
The same side. You
Yeah, exactly.
So if like mu is like 1, 1, 1, 1, 1, you're just the usual, the biggest strata.
Yeah, exactly. So if mu 1, 1, 1, 1, it's gonna be just Sn, quotient down by Sn.
If it's mu says n0, what is that?
N0.
Yeah. So when you write S mu, you mean what? S to the power mu?
Yeah, so I view mu as a set. As a set of k elements where k is the length of the mu. So if mu is equal to n, so
just a set of lengths 1.
so this is just set of length 1.
Okay, sure.
As a number of columns in a Venn diagram.
Yes.
What is S called mu? S called set?
Yes.
It's the number of S to the number of blocks. Yeah.
Okay.
So this is I view
Number of blocks. Okay.
no columns. Yeah.
I see. Two different n's here on the top. Like there is mu equal to 10, and there is n number of numbers. Not number of.
No, yes. Okay. So if it's a column,
fine.
Yeah. If it's a column partition, you just
Okay. So
the point of introducing this insertion is that you're not looking at all possible maps from C to S. You won't say here's the point of orbital Z.
Yeah.
Better map to something where m points cluster together.
yeah.
Okay, so it's like a restriction.
Yeah, so I mean,
Then we also evaluated this. Subject you put, not you put ramification, not your evaluation.
yeah, but I have evaluation on in the C. So yeah, so each ramified point in C prime is canonically marked in some sense. It's given, and it defines the length mu evaluations to S.
So what is canonically marked? The C
So
map to S.
yeah, so if you take so if you take now the pre-image of P, right, the fiber of P, so this is the ramified points at P. So those sitting in C prime, and those you can now you can define evaluations. So you can define evaluations with respect to this. So you view these fibers as a marked point now in C prime, and you define evaluations of these marked points to S. And when I say what are insertions, so the insertions are equivalent to the specification of a ramification point at P, and then this ramification point gives you some fiber, and you pull back some classes with respect to that fiber. And you have also like some order on the, because there is a, I mean, you have order on the ramifications, right, on depending on the length, and so there is also order on evaluations, I mean partial order. Okay. So what I want to say, the orbifold stuff is a bit funky, but okay, what you it's good to keep in mind So you know when you consider curves to the Hilbert scheme of endpoints, so what are the classes here? The classes are specified by Nakajima basis, right? In particular, what is it's specified by some partition with a cohomological class attached to it. You should view, so in the sense that the insertions in the case of a Hilbert scheme of endpoints corresponds to this cohomologically weighted partition, which is given by some partition with some class beta attached to it, right? So let me write more of this. So it's mu1, beta1.
So this beta lines are classes in S?
Yeah. And so by Nakajima operators, these guys span the cohomology of Sn. And so the same you have here. So to each partition, you can attach an insertion. The partition part of this cohomologically weighted partition will specify ramification, and the classes will specify the classes that you pull back with respect to the markings that these ramifications give you. So it's, yeah, so.
So you're saying there's a certain bijection with the bijection?
Bijection with what?
The marking, the Nakajima basis with the.
Yeah, so what I'm saying, the insertions here, insertions correspond to cohomologically weighted partitions. So you have a partition with a class attached to it.
Yeah, but I don't understand what you said there. Insertions are ramification with what F mu classes?
L mu length. So let's L length.
Yes, the number of blocks.
Yeah.
Ramification with LU classes in S.
So it's just I'm just saying that what is the insertion? It's just a cohomologically weighted partition.
Okay. I see. You want these branching points to certain cycles.
Yeah, exactly.
But it's not complicated. Think about, what's a curve in Hilbert scheme of points? It's like a degree n scheme, which is flat over the gate.
Yes.
And imagine the degree n scheme is just, it's like it's a curve. And then when it hits, when it's supposed that points supposed to come together with the divisor, over a point between the divisor. Points come together on the divisor, the sum multiplicity, there will be what? There will be like a subscheme of that length, part, that thing. And the curvilinear subschemes of a given length, that's like an open dense set within what Nakajima operator does. Nakajima operator does says put some blob of some thickness. But the blob of some thickness is open set there is formed by curvilinear schemes, things that are just tangent to a curve.
What do you mean by curvilinear system?
So in the Hilbert scheme of points, like a subscheme doesn't have to lie on the curve. It doesn't have to be one dimensional. The one dimensional one, they're open set. So open and then. In one they have endpoints come together. So that's just saying, I have that. The nicest possible locus in the Hilbert scheme. In this Gromov-Witten theory of symmetric of the Hilbert scheme, the nicest possible locus really looks like just really what Denis writes down. You have a curve degree n mapping to your base curve, ramified and tangent. This is tangent to some. What does it mean? Tangent. If it's tangent to the point of some degree, it means you have a ramification of the degree. Yeah. Since this says like what you expect that the correspondence of the nicest locus somehow magically continues.
Yeah, I understand the nicest locus like the covering curve, the degree and cover of S is like the generic distinct ramification points. That was the nicest.
No, I mean they have to be distinct. It just says over every ramification point. I'm telling you, I'm telling you that you're some. What does mean ramification? It's an tangent to the fiber. Yeah, that's right. The tangent to the fiber with the order, which is the length ramification.
The length of the ramification.
Yeah.
So if it's a simple ramification, just that. That's
Yeah, 2 points come
2 points.
together.
Yeah. And what's the more general one?
We have 5 points come together. The nicest locals, they'll come together along a curve, along the curve in the fiber.
And the partition describes the tendency.
Exactly, so it says how I'm tangent to the fiber. Unification of this curve is the same as tendency to the fiber.
So there's just one number, the tangency order.
Exactly.
That's
Yeah.
like the height of that column.
Okay.
Yeah.
Okay, cool.
I mean, okay, I don't know if I should.
You can draw a picture, it's worth 1,000 words.
No, I don't know if I'm just afraid that I will confuse. So, I mean, I want to repeat.
But the same picture, the same as, you can do it the same as kind of 2 dimensions, 1 plus 1 dimension. That'll be easier. Because the 3rd dimension plays no role for you in this discussion. Imagine you have a curve in C cross C.
Yeah.
And then whenever it's ramified over the base, it's the same as the tangent to the fiber.
Okay, let me. Did you understand?
Yeah, I understand.
Yeah, so I mean, okay, what you have to take away from this is that the maps, so essentially Gromov-Witten theory to the symmetric product can be defined as by the following data. It's some cover of that C and with a map to S. And the ramification is some kind of insertion. If you assume that S is a point, so you just have covers. You don't have this extra data. You don't have a map to S because it's just a point. So in particular, the theory in this case becomes just covers of S, of C. Covers of C.
It becomes this kind of admissible cover, right?
Yeah, admissible. Yeah, sure. Exactly, yeah. I'm trying to, I don't want to, there is some condition on at the node you also need some condition. You allow some ramification at the node as well. So doesn't matter. It's a little complicated. So what I want to say, why Hurwitz? Well, because if you just assume S to be a point, then literally the kind of the Gromov-Witten theory of a symmetric product of a point is a Hurwitz theory. Hurwitz theory is just covers of curves. And so this you can view, so when you consider actually now symmetric product of some high dimensional variety, you can view it as essentially Hurwitz. It's Hurwitz theory with a target.
So when you say Hurwitz, you mean you allow branching or no branching?
Yeah, branching is allowed at the markings. It's covered everywhere but at the markings, because at the markings you view branching as an insertion.
So your C is not a naive C, some C is a
markings, yeah. Okay.
When you write P, you mean not just a single point?
Yeah, I mean, yes. Yeah, I mean, all this orbifold stuff is a bit complicated. Okay, so let me just conclude that what I said. So we have this modular space of maps from C to the symmetric product of S, and essentially this you can view as maps from, I mean, as previously, so if you allow just covers, so if you don't allow ramifications everywhere apart from mark points, I mean, you will not get a compact space unless you allow your C to bubble off some bubbles. So in particular, so what I'm writing now is the following. So if you, the Gromov-Witten theory of a symmetric product with a fixed curve is essentially can be viewed as maps from this the cover of this C tilde to S, such that this is a degree n cover, and where this C tilde is a bubbling. Yeah, let me now just draw a picture, right? So you have it's as before. So you have this bubbling now. You have your curve C, and above that curve you have another curve C prime. With some maps to this bubble, and all of that is a tau, so cover, with ramifications allowed only at the marked points. Okay. So this is what the space parameterizes, and the map, sorry, and the map to S. No, you don't have.
So where is the bubble?
This is a bubble. P1 is a bubble.
Why, if I fix my C, why do I need to invent the bubble?
Well, because it's the same problem as with the Gromov-Witten theory of any other. I mean, it's just not proper otherwise. You can imagine the situation where you become, in a limit, you become degenerate.
But you mean your C, when you fix the C, you mean you fix the complex structure on C, or what?
Yeah.
Fixed complex structure on C, you still have bubbling?
Well, it's like before. It's like in a Hilbert scheme. I mean, it's even if you consider maps from C to any variety X, the moduli space is not compact.
Okay.
So you have to consider bubbles. Yeah. You have to consider MC bar, which is the bubbling.
I confuse myself with like nodal degeneration versus bubbling. Bubbling is like you're squeezing your maps into some weird corner.
Yeah. So this is one moduli space, and essentially you have to view it as a. So this is in some sense this space is you have to view it as this space of maps to the Hilbert scheme of endpoints.
So that's the kind of question. So you wrote C prime over C, let's say the tilde everywhere. You have some genus over this P1.
Yeah, sure.
Why you not?
Well, if it's not, it's just if it's P1, it's, well, you can also have P1 is going to be ramified.
So you're saying in general, your C prime maps can have extra branching point, not just at its P, it can have other branching points? Not only at your
Yeah, it also can parent a node. This is I was.
Yeah, I'm not asking for that. I'm saying we'll have in the original theory when we have a C prime maps to C.
Yeah.
You are requiring some branching point at P, but that's not the only branching point. You do a lot some other branching points.
Okay, yeah. I mean that's a. Let me come back to that. Okay. Yeah, I understand your confusion. Let me come back to that a bit later. So. Yeah, you're saying that if I fix the genus, how can genus can change, right?
No, that's not my conclusion. My conclusion was like, we'll have the covering C prime to C. Suppose you have no marking P.
Yeah.
You still allow branching.
No.
You don't allow branching.
Yeah. I will actually allow branching. Yes, I mean I have to allow.
I'm saying like this piece, like it's forced some minimum.
Yeah, exactly. You have to allow simple branching, otherwise this theory becomes I want to say, yeah, I mean, it's a bit confusing. Yeah. So you have this moduli space. I'll come back to that. Okay, you have this moduli space of maps from a curve to the symmetric product, and this is just this configuration. So it's just some covering with a map to S. So, and as before, well, you have a different kind of situation, right? You can now disregard all these rational tails, and you can consider, well, you can allow like a different kind of a behavior where you forget about the condition of being a cover. You allow your map from C prime to C to have contracted components. And you also allow it to have some ramification outside of a mark point. But what with the sum up to S? But what is this? What is data? Well, this is exactly the same as considering the Gromov-Witten theory of S times C. Okay, so you don't have any conditions now on your map. It can be as degenerate as possible. You have a fixed C. You forget about its bubbling. As the price that you pay is that you have contracted components and ramifications outside of mark point, and you have then an extra map to S. But this is exactly equivalent to the data. So this is equivalent to the data of some curve C prime, just mapping to the product S times C, no conditions, right? So I mean, this data is therefore just the moduli space of stable maps.
It's not entirely true, right? Because you still take relative. Don't you take relative A?
Yeah, I mean, if you introduce markings, yeah.
Well, now we're saying mark points. You mean this kind of this kind of orbital point?
Yeah. Well, it's the same. I said forget about orbifold. What I want to say is that orbifold is just the same as just a specification of a ramification.
Okay.
It's the same as considering requiring your ramification to be of a certain kind over this mark point, and this is the same as this relative condition on a Gromov-Witten theory.
So okay, let's say in a simple case, like suppose you only have one ramification point.
Yeah.
It's a simple ramification point. 2 points come together. Cover. And then do you allow more ramification point on your base? Yes or no?
No, I mean, in a Hurwitz theory, you don't allow.
You don't allow.
You allow them. Yeah, you can allow them. You can allow only simple ramifications. So that's what I want to. Okay, I mean, let me. So in a Hurwitz theory, you don't allow any ramifications. You can allow just simple ramifications, and this will be an extra data. This will be an extra class in some sense. This number of simple ramifications will be like an extended degree of your map. So let me say. So what we want to do now. So as before, so we have this situation. So maps to symmetric product. This is maps from this covers, and with a map to S, and we have this situation. Just arbitrary ramifications to C with a map to S.
Sorry, I'm just a little bit like not so sure. It's not just any map to S cross C, right? You also want this to be a branch cover when you project to C.
Yeah, it can be arbitrary. What I'm saying. So this is completely. I mean, this is the opposite to that, right? Here you have only degree n covers. You allow branching at P. Here you have arbitrary ramifications, but you also allow branching at P. Branching in P will have a different meaning to the rest of ramifications. It will be some kind of insertion.
And you also allow them contract the components.
Yeah, everything.
That's much bigger.
Yeah, it's no problem. I mean,
But you allow this when you map to C, you map to a point, that you allow that? You don't allow that.
which map to
I mean,
C?
you're in Paris, so your C prim, you map to C, it just become a point.
You can be a point, yeah, but
C prim map to C to a point.
yeah. Yeah. So let me. You remember I was drawing last lectures. I was drawing these pictures. I have S times C. I have some graph of some map, and then here I had this contrast.
I know you can have some components mapped to a point, but
Yeah.
you don't want the entire guy mapped to a point.
No, you can. Yeah.
There's some sort of degree here.
Yeah, it will be equivalent. It will be equivalent to this picture.
So you do allow this.
Yeah, you can of course allow that. Yeah. It's just degree 0. I mean, it will not be to C. It will be to point in some sense.
Okay.
No, it will not. It will not be like a maps to symmetric product. It will be like maps to a 0 symmetric product, which is a point. Well, it's like this. This is maps to the moduli spaces of sheaves of the Chern class 1, 0, 0, which is the only stable bundle in this Chern class is just a structure sheaf.
Okay, so you do really mean M bar is the
M bar, yes. So this picture is exactly the same as that, and this picture was exactly the same as this. Okay, you understand analogy?
Now this is more like the Gromov-Witten is more like DT.
Yes. I mean, yes.
I think technologically it's better to call these points P punctures, because then you don't have to worry about anything. You have a map unramified outside of a puncture.
You require certain ramification.
Oh, ramification is something else. It's just P, it's nothing much happening. It's unramified outside. And the puncture.
So we have these two situations now, right? So this is exactly the same as MC to the symmetric Hilbert scheme of endpoints and the Hilbert of S times C. Okay, now there is a bug here, or it's more like a feature as well. So by Riemann Hurwitz, ramifications, if you know your ramifications and the degree, genus of C, you will know the genus of C prime, right? As soon as your étale cover.
If you use that vulture notation, you wrote two more things up there. And that one is the same as the.
I mean, it's an analogy.
Oh, the hue.
No, but I think it's in general, right? I mean, if you think of what's for any map there's ramification divided, that's the Riemann Hurwitz full.
Yeah, exactly. Yeah, I mean, I was just inexplicit in what I was saying. So, because I always said that this is unramified, while here, when I moved to this situation, I said that you can have arbitrary genus mapping to C. So what now, so genus is a parameter automatically here. But genus is a parameter in MS times C. So we have to allow simple ramifications as well. So here now the class. So now this is a map. This will be configurations like that, but you allow now m simple ramifications. Where simple ramification is the simple ramification is the one that's given by. So it's the closest one to being unramified. So it's simple ramifications is the one that over type z goes to z squared.
But in principle, this is just you just fill up you have some kind of observable, and you have to fill up to help to integrate something in the given genus. So, but you pick any ramification you want to fill up with two.
I was thinking like in real life, don't you have some sort of situation where simple application degenerate into worse
Right,
ramifications?
I mean that's also how you always allow any number of ramified point of whatever type you want to fill it up with two. These are still at a given point, right? These are simple.
Huh?
They're at moving point.
Yeah, they're allowed to move. Yeah. So what I wanted to say that is like the correct thing on this side. I mean, if you allow genus to vary on this side, the correct thing on this side will be to allow simple ramifications. So m becomes, so there are two parameters, two discrete parameters. Beta is a class in H2 of S. So you fix a class of this C prime with respect to S, right? But you also fix the number of simple ramifications. And on this side, you also fix the class with respect to S, and you fix a genus, but it's the same as fixing a number of simple ramifications, or like it's the same as fixing the degree of a ramification division. So genus determine genus and M determine itself in via Riemann-Hurwitz. So in particular, we can just write M here.
So here you're summing over all the degree, like all the degree n covers summing over n. Are you summing over n?
Yeah. So n will be degree n covers, but here n will be just the degree with respect to C.
Okay. So you specify some constraint.
Yeah. Oh, where is it? So, okay.
So you're saying these hidden ramification points,
Yeah.
and it's determines the genus, right?
Yeah, exactly.
Of course, that's
So,
but how can this be compact anymore? We require this simpleness.
yeah, you can still allow it to, it's fine. It's compact.
It means they go in the bubble, right?
Yeah, I mean, if they come together, they go in a bubble.
You just bubble again to put them apart?
Yeah, exactly. That's what you always do.
But they're simple, right?
Mm.
I mean, effectively, they replace if they come together with the
function point
bubble,
interface.
but effectively they get triple ramification because that bubble will be glued to the mother curve by triple ramification. So that's
Okay.
then you get.
So let me now. It's a bit confusing, but let me. So let me now introduce a little notation here to bring the story on the same kind of in the same language as the quasi-map language. So the notation I'll write like that. C goes to symmetric power of S to mean definition to mean any map from some curve C prime to S times C. So in sense, any map from C prime to S times C is some kind of a quasi-map. Oh, it's defined generically. It defines a map to the symmetric product because generically it's unramified. Only at some points you get ramification, And but generically you don't have any ramification. So generically you indeed get a map to the symmetric product. So this notation is perfectly justified. And so you can view any map from C prime from any curve C prime to S times C as some kind of a quasi-map to a symmetric product.
You do require embedding C prime to S prime C, or you allow?
No, it's any map, any map. You mean C prime go?
Yeah.
No, it's like that.
Oh, so I think the node, for example, when you collapse the node C prime to C, something collapse, but when you map to S, that same thing can also collapse.
Yeah, that I don't understand. You mean this can whether that can be collapsed to S?
Yeah.
Yeah, sure. It will just of course. Yeah.
Okay.
So what I'm saying is that I'm defining. So, I mean, I'm defining this kind of a quasi-map. It's not quasi-maps. I'll call this. So the notation. Huh? Sus? What? Huh?
I was afraid you're going to call them pseudo-quasi-maps.
I'll call them ramified maps to. No, actually, okay. It's in a paper. In a paper, it's called like 0 plus admissible maps. But I think the better name is ramified maps to symmetric problem. I mean, it's justified, right? Why ramified maps to the symmetric product? Because it's exactly ramified maps to the symmetric product.
You can have components. You can have collapsed components.
Yeah, sure, but generically you still have ramified, yeah.
So why is it not?
Yeah, sorry, yeah. You mean because the collapsed components are not ramifications? Yeah, I don't know. Yeah.
Why is it not enough to consider like one-dimensional subscheme in S cross C, where you have to calculate maps? Data of maps.
Well, but it's completely different story. I mean, you have maps are.
I thought the point is like using the graph is like.
No, but this is not graph. This is a completely different story. This is not graphs. I mean, I'm not considering graphs here. There's different. I mean, not all subschemes are graphs. The same way is not all.
Yeah, but you take closure of those nice guys. Why not?
I'm not taking any closure. What do you mean? No, it's just arbitrary. What is the confusion? So it's just arbitrary maps from C prime to C with a map to S as well.
Okay. So I guess my confusion is like, why do you need such so many like extra stuff?
Well,
okay, go ahead. I will see reason.
No, I mean you'll not see a reason if you don't see it now. But it's.
I can see this.
Well, I mean, it's exactly the same in this situation, right? I mean, why can't you just consider graphs of maps in the product S times C? Well, it's going to be far from compact.
Yeah, but I can say, okay, I can look at the embedded types. Like,
yeah, but it's exactly the same as considering just embedded curves.
Why do you allow that?
I guess the whole point of Gromov-Witten versus DT that you have maps or you have graph or you have subscript.
Yeah.
And those are you can
Here, so I'm saying you are doing more Gromov-Witten like things.
Yeah, that's Gromov-Witten like thing.
Yeah, so let me. I mean, if you consider, just take any x, and you consider maps embeddings to x. I mean, this is never going to be compact. I mean, the whole point of Gromov-Witten theory is to fix the fact that this never will be compact. Well, because you have, you can degenerate to arbitrary singular thing, and you cannot map always like isn't it?
But I mean, just to think about some kind of curve in X. You can have 2-to-1 map to that. The Gromov-Witten theory is just really it's like we use 2-to-1 thing.
Oh, okay.
And if you want a subscheme, then you have to have some kind of subscheme with some kind of fixing.
In some degeneration, you can have like two things holding together.
Yeah. And then you have to. I mean, this is different. You have two different things living at the same point, and there you have to specify which way.
Okay, thanks.
Which way.
I revealed some fundamental ignorance of me as well as Gromov-Witten, why bad things can happen.
Yeah. So I'll call it ramified maps. So just to put everything in the same notation now, so we essentially what we have to consider, we'll consider the wall crossing between unramified theory of symmetric product and the ramified theory of a symmetric product. So this is just ramified. This is just ramified maps to the symmetric product. Okay. Ramified. So, but again, so what is that? As in case of quasi-maps, we'll have, so here you have that behavior, right?
Substrate of C, you have also fixed as C fixed.
Sorry, yes. So, so here, we're calling it, this is, the behavior over here is like that, right? The behavior on the other side is like that. So in between, we'll have to introduce a mixed behavior, just like in the case of quasi-maps. So you allow, so what you trade essentially rational tails for arbitrary ramifications, right? By ramifications, I also mean contracted components. And so you have to introduce something, some kind of moduli spaces that interpolate these two extreme situations. So you'll have some kind of a moduli spaces where you have both rational tails.
They are gradually folding up the rational tails.
Say again?
They're gradually folding up the collapsing rational.
Yeah, essentially here it's a bit easier than the Hilbert schemes because I mean, what is the difference between that and that? You just contract these P1s and then you get a ramified map. So there is in some sense, well, there is a map, at least in some locus. Well, okay. In some situations, you really have a map from moduli spaces of unramified maps to moduli space of ramified maps. You just contract. Well, actually, in all cases, there is always a map from unramified maps to ramified maps by contraction of P1s. But in this case, I mean, in this case, actually, so like Hurwitz, for example, if you take just covers of curves, this will be irreducible and smooth variety. But if you take Gromov-Witten, so if you take stable maps to curves, it will have many components. So Hurwitz situation is always like it's literally a better compactification in this case. While in case of this DT Gromov-Witten stuff, quasi-maps, it's not clear which one is.
Which one is Hurwitz?
Hurwitz is this one. By Hurwitz I always mean covers, right? I mean with the situation where you have covers. So you will have, so between these two cases, you have this intermediate kind of moduli spaces that allow both P1s and so rational tails and ramification. Huh? It's called epsilon ramified or epsilon admissible. That's a good name for that. So size of P1. So as before, what you do is just you restrict the size of P1s and the size of these ramifications. Like in the, this preliminary definition. I will now define what it actually means.
So what's in principle this kind of model like this you can consider it for S being arbitrary dimension.
Yeah, it's arbitrary dimension. Yeah.
And this is this kind of wall crossing will happen in
this holds. So the level of generality in this situation is it holds for arbitrary X. Yeah. While the level of generality in this quasi-map is that it holds for arbitrary moduli space of sheaves, but here you have like extension to the different direction. It holds to arbitrary symmetric products of arbitrary X. Even though, of course, I mean, I don't know what. I don't know what.
How if you sum up, you want to sum up overall general.
Yeah.
Then the first surface case is special because then it's only then that the direction dimension is independent.
Because C times C, S times C is three-dimensional.
Not just because in the virtual dimension is three.
Yeah.
Three-dimensional space.
Hmm.
This is somehow true for fixed G.
Yeah.
This is what you're doing is somehow just for fixed G.
No, genus. Yeah, it's a fixed genus, but you view genus as a degree in some sense because you can specify genus by the degree of a branching divisor. So you view it. I mean, the right point of view in this situation is like an extra degree. It will be like a response. It's on the Hilbert side, on the DT side, it will be the exceptional class or the Euler characteristics. Yeah, but I mean, this works for a fixed degree. Yeah, sorry, for a fixed genus. So what is the time actually? Do you have?
11:20.
Oh, it takes a long time. I'm sorry. So what I want to say is that you have this. So you want to introduce some kind of a mixed behavior, right? So you want to have some tool to measure how ramified you are. Well, but there is a very basic thing that you can construct, and this is called I mean it's been mentioned a couple of times already, and it's just called a ramification divisor. So what you do, I mean, how you measure ramification, right? Ramification is measured by the relative cotangent bundle. So if you're unramified, you're locally isomorphism. So if you pull back the cotangent bundle, it's isomorphic to the cotangent bundle upstairs. If you're ramified, so when you pull back the cotangent bundle from the curve to another curve, it will not be isomorphic. And so the measure of this non-isomorphism is just the complex. So you have a canonical map. So you pull back omega 1 from a curve. You have a canonical map to omega 1 of C prime, and you consider this map as a complex. So it will be generically it will be isomorphism because generically you're unramified, but at some points something funky is going to happen. So you can see that this complex is actually concentrated, and it has its support on a zero-dimensional. It has zero-dimensional support. So what you do now, you just push it forward with respect to the same map, or the right push forward, and then you take. I mean, will be some zero-dimensional sheaf on C, and this I call the branching divisor of F. Okay. So what this does? So if you have, let me just. So what it does, if you have contracted component like that.
It's not so great to denote the map F and the projection F also by the same letter.
It's the same map. I'm sorry, which one?
The map
FC.
F goes to C.
Yeah, but this is FC. Sorry, this is FC. So this F can be factored as a map FC and FS. I mean, I can call it phi as well, but I don't know. It's gonna be.
That's a restriction.
Huh?
With a restriction.
Rather FS would be the opposite order. First.
Yeah. So you just take one. Yeah. So what is this branching divisor? So if you have a contracted component, this branching divisor will be of degree 2g minus 2, where g is this g of the contracted component. And if you have ramification, So if you have some ramified point, let's say ramification is of degree z goes to z ze, and then the branching divisor will remember this as e minus 1 at this point. So what I'm saying is that you have a point, call it, what is a good point? Call it point S, I'll call it point B, call this point B prime. So what I'm saying is that if you restrict now your branching divisor to the point B to which you contracted the component, it will be of degree 2g minus 2. And then if you restrict it to point B prime over here, it will be of degree e minus 1, where e is this degree of ramification. Okay? So this is a, and you use that. You okay?
But the same notation for two different phenomena.
What do you mean, same notation?
Capturing the five. Yeah.
But it's totally fine if you can suppose you can perturb this cloud component, smooth it out, and we'll have the total ramification stay the same.
Yeah, that's nice.
Yeah, you mean the total degree of the branching divisor will say the same. Yeah, but the degree, but so there are two kind of things here. There is total degree of a branching divisor on each component of a curve downstairs, but there is also degree at each point where you have a ramification. And of course, if you smooth it out, then degree at this point will kind of disappear. It will disappear.
How do you slowly?
Huh?
No, it won't disappear. That's the topology. It's not how really
Distributed.
Yeah, it will distribute it, but it will not. Yeah.
Yeah, it will be generic. It's possible generic perturbation. That will be just some bunch of simple things where this e is equal to, and that the total number of simple things you're going to get is
So let me now define
Epsilon.
epsilon ramified. So we have a so definition. So f a map to C from C to C of S is a epsilon ramified if, so firstly, for all ramification points, in this case, I mean, okay, it's branching points, right? Down on the base is called branching points, and down up it's called ramification points, right?
every point is the support of the branching divisor.
Yeah.
Multiplicities of the branching
Yeah.
divisor at most.
Yeah. So for all,
It's like in this high-dimensional algebraic geometry. There's like the bound the multiplicities of the divisor.
I don't know what you're referring to.
No, I mean when you do this, whatever definition of whatever singularity.
Oh yeah, okay. Oh yes. Yeah. Something like that here as well. Yeah. So for all B in the support of this branching divisor, or for all ramification or branching points, you have the following condition. So if you so epsilon will be just a positive number. So you have the following condition. So the branching, so the degree of a branching divisor. Okay, there is extra data that you have to add. You have to add also the degree of this contracted component with respect to some upper line bundle. So the degree of a branching divisor plus the degree of of the contracted component if there is one. If there is no contracted component but just ramification, you set it to 0. It's less or equal to. Here I have to do exponential because you remember we allow simple ramifications, so you can actually allow ramifications of degree 1. So in particular, if you wanna your epsilon to go from 0 to infinity, which I want for notational reasons, I take an exponential. So at 0 it will be 1 because I allow simple ramifications. Okay, it will be confusing. So I'll take epsilon from 1 to infinity, and I'll take epsilon here. Sorry, 1 over epsilon. Again, it's just conventions. And then also for all rational tails in the C, you have when you restrict this guy to the rational tail, and then you add the degree. So you add the degree of these guys with respect to the line bundle over here. It should be greater than 1 over epsilon. So where L is some ample line bundle on that. And then there are usual conditions that you require the automorphisms. So this is to get rid of bridges, unstable bridges. You require the automorphisms of your map to be only find too many automorphisms. Okay. Okay, probably let me write it here. And so now you define this ramified epsilon stuff. So ramified epsilon maps the symmetric product. So this is just epsilon ramified maps to the symmetric product. And so you can check again by definition that if you take epsilon 1, this is equal to this ramified maps, and then if you take epsilon infinity, this will be unramified maps. And then in between, you have this epsilon ramification that interpolates. Okay. Yeah.
Can we write this like epsilon stability condition as like Hilbert Mumford on some like local chart on the stack with ramified maps or something? Or do you just like guess that this is the right thing?
You mean as a like the JT kind of a?
Yeah, like some like local GIT chart on the stack.
Yeah, I don't know. It's massive stacks that are really nasty, right? I mean, it's like I don't know if whether it. I mean, first I don't know whether it's possible. Secondly, I don't know if it's even productive to do that. I'm not sure it's actually that it's possible because it's not controlled by the JT kind of a stability overall. Because it's like massive stacks with many components. You don't know like what dimension those components are. I'm not even sure that locally probably you're still JT here, right? I mean, you always locally JT. I mean, etal locally. Yeah, but I don't know how etal locally is, whether it's good enough or.
Yeah. I just want to say, like, right, I mean, it's I guess it's clear where it comes from that you like exchange expense of rational tails and ramification. But you wrote this down and then like check that's proper.
Oh yeah, yeah, sure. Well, properness is not difficult to see in some sense. I mean, what you always do, you can always take like some kind of ramified limit, and then you can just modify it to. You can take like the most ramified limit ever by the properness of stable maps, and then you can like blow up consecutively to get the epsilon ramification, the desired epsilon kind of stability. So it's, if you understand like what's going on, it's actually not difficult.
Well, the kind of properties and stuff, it's enough to assume that maybe we should check the space.
That's also true, yes. But I guess an argument is also abstract enough to not to kind of consider any specific properties of a given target variety. Well, I mean, yeah, you rely on the properness of stable maps, which in turn rely on essentially specializing to PN, and then.
Well, I'm trying to say, I think that you can probably bring it super close to just this sort of Hassett modulation.
Yeah, exactly. This is I mean, but this is exactly the Hassett. I mean, this is this condition is exactly the Hassett kind of multiplicities. You just add.
If you map to some huge projective space, it's more or less you forget the map.
Yeah.
Some stuff floating around.
Yeah, but yeah, I mean, without these two other conditions, I actually.
Those are kind of, those are also come as some kind of insertions. So those are kind of, like a sort of hyperplane sections in the projective.
Yeah. Mm-hmm.
With some kind of extra mark point, they also allow, you have to count their monsters.
Mm. Yeah. Well, in fact, so when I started doing that, I realized that there was a student of Harris. I don't remember the name of the student.
Smith?
Huh?
Was it Smith?
No. It was a complicated surname for the reason that for that reason I couldn't remember it. And he actually started in his PhD the same kind of situation, but instead of allowing contracted components, he allowed arbitrary singularities in the source curve. So there is another situation where you kind of pass from unramified situation to ramified situation, but ramifications in this case becomes also like worse singularities, worse than nodal singularities of a curve. So you don't allow contracted components by the price that you pay. You kind of in that contracted component you add like really bad singularities. And somehow I think that was left unnoticed because it's like you don't have any abstraction theory and everything, so it's kind of you cannot do much with this kind of model spaces. But the stability is exactly the same, even though he didn't have the target stability. I mean, he didn't have the target S, so he had just this Hassett type stability for this branching device.
What's the name?
Hassett. Well, he constructed this marked model space of marked curves with the multiplicities at markings, and you can kind of vary the multiplicities. So you allow in these model spaces the markings to come together as soon as if they're of right multiplicities. And it kind of gives it's interesting because it gives when you vary this multiplicity stability, it gives some kind of MMP for modeling of stable curves. Yeah. Okay.
So intuitively, these expressions are like the size of something.
Yeah. So it's just a size. So it's just. You can say it in words. Actually, you can just say, well, at each point, I restrict the genus of a contracted component and the ramification.
That's like the first component.
Yeah, this is the first part of the definition. The second part of the definition is that if you have a rational tail now, you also restrict the size of this rational tail in terms of how many ramifications this rational tail carries. Well, you want to interpolate between ramifications and rational tails, right? So you allow for each epsilon you allow ramifications of this size lower than something.
About the degree part of the.
Yeah, big degree part, because you can. Well, you have now situations where, for example, you can have.
Is that capture the genus or what is it?
No, you mean the degree, the second one? No, it captures something else. So you might have, for example, you have like now P1 over here. It contracts. If you don't have a target, this is not allowed. But if you have a target now, this P1 might map non-trivially to the target S. And so you have to take that into account. So you have to assign. So because you have to assign some kind of a degree to this P1 that measures not only its contraction but also measures how big it is with respect to this S. Yeah. Oh, okay.
So the bigger this degree number is, it's like the more curved the things in the target has.
Yeah, exactly. Like how big it is in the target S. Yeah. Well, if target was just P2, let's say, it's like what is the degree of your curve in this P2? I mean, just that in P2 you can canonically define degrees. So okay. So let me now. Okay, what is the? Let me just say a few words about this wall crossing now. I mean, it takes exactly the same form as this quasi-map wall crossing. Instead, you take what is called probably, I don't know, is it a good terminology? Gromov-Witten vertex. It was used, right? So what you consider a modular space of maps from curves to S times P1. This has a C star action as before, right? Oh, you also let's introduce classes. So you have class B and class M. So M is equivalent to the genus of the source curve. Let me recall. And at this point, actually, just a remark. At this point, it's kind of nice to take the genus, because genus is not additive, but the branching is additive. So it's yeah. Okay, and so as before, you just take this. You take the vertex. It's called Gromov-Witten vertex. So this is some C star fixed loci, where you don't have no ramifications. That's some kind of how you allow ramifications in infinity, but only those that come from the mark. I mean, the fact that it's a marking.
But it's just really going to be some kind of theory of maps to S.
Yeah, exactly. This is the just Hodge integrals. For the Pets, it's exactly double Hodge integrals. Well, let me write no ramifications. Even though you allow ramifications, but you don't allow like contract components, for example. So how does it look like? So you have your P1, and here you have so this will be the picture for this So this the picture for this app.
It's really just Gromov-Witten theory of S, in which you have mark points with cyclones, those mark points.
Yeah.
One more factor.
You mean this guy or in general?
Just in general.
So it's gonna be just relative. No, it's gonna be
relative. Just look at this picture.
Ah, yeah, yeah.
Here, we have a map to S.
Yeah, yeah, yeah. Ah,
and
yes,
then
yes.
that's a mark point, and that mark point has side classes.
Yeah, yeah.
And we have from insertion here we get one
Mm-hmm.
more hash block.
Yeah, exactly, exactly. Yeah. In the end, it's what it becomes. So for Del Pezzo, for dimension constraint reasons, you just have like double Hodge classes on a model of curves. So this is called, okay, I don't know, it's called Gromov-Witten. You can call it Gromov-Witten vertex. Okay, and so in the same way, you just define this I function. The I function will be just a
If Sasha were to walk in by chance into this talk, he'll say that he calls this part, I think he calls J.
J. Ah, this J.
I was like the hypergeometric stuff, and right, yeah, I think J.
No, but yeah, this is not Quasimodo, so it's like
Yeah,
something.
yeah, that's, I think he'll say that
Yeah. And so what is this? Is again just evaluation. Well, you have evaluation map that just sends this B2. Well, it sends to inertia stack. And so you push forward as before, just the virtual fundamental class over the normal bundle.
Just make sure what is the beta and beta is something.
Yeah, yeah. So let me just. So beta is just some H2 of S. I always kind of suppress. So there is H2, the class with respect to the first component, and there is also degree with respect to the first component. Second, sorry. Beta is a degree with respect to that component, and there is n with respect to that component, which is like the sim n.
Yeah, right.
I kind of suppress it always from notation because it's inexplicitly it's sim n is over here.
Okay. So you're requiring the C prime to map to S images in the beta.
Yeah, yeah, yeah. So I mean, it's just a Kunde decomposition. You can decompose. Yeah.
M is an equivalent degree.
No. There's no covariant. Which? Sorry.
So what is M?
No. It's equivalent to genus. Sorry. Equivalent to genus. It's equivalent to genus of FC. Sorry, of FC prime. Yeah. Sorry. Okay.
So what is epsilon?
Huh?
Where is the dependence on epsilon?
No, there is no dependence on epsilon over here. It's just it's vertex. It's well, you can make a dependence on epsilon, but it's for what I'm gonna write, it's not necessary.
But M literally is what?
It's just number of simple ramifications. It's degree of a branching divided.
It's a multiple numbers or is it a single number?
Hmm?
M is a single number or is it?
No, it's a single number. It's just a degree of branching. So in the case of unramified theory, this is just number of simple ramifications. In case of ramified theory, this is equivalent to also to genus. Yeah.
It's always equal to genus.
No, it's not equal. It's not. Yeah, it's not equal. There is a formula that relates that way. Oh, so let me. Okay, so there is also this mu. I'm sorry for notation because I was also writing mu for the partitions, but sorry. So mu beta m is just the truncation again of this guy. And so what is the so this is by non-negative powers of z. where z is so it's z is the equivariant parameter over here, and we expand at infinity. Okay. And so what is this Gromov-Witten Hurwitz ball crossing? Well, it's exactly the same as before. Let me just write a sketch here because I don't have much time. So if you take brackets on one side, so for ramified theory, so this is equal to the brackets on the other hand side of unramified theory plus these correction terms where you insert, now you have extra insertions, and you insert this mu evaluating yes at psi n plus 1. Sorry. For some classes, okay. So this is this is the ball crossing formula. So if you take it's just same as this Quasi-Map ball crossing. So if you take unramified, so ramified theory is equal to unramified theory plus unramified theory with these insertions that come from this class mu, which is what?
No.
So you have mu. This is mu is this truncation of I. I is some bunch of classes in H star with a Z. Z is a covariant parameter. So you insert mu such that you substitute psi classes in this covariant parameter Z.
So one is the epsilon.
One is epsilon. One is this ramified. One is
the most vertical.
yeah. This is which is equivalent to which is equivalent to m of s times c. So this is Gromov-Witten theory of so this is Gromov-Witten theory of s times c. Well, this is Gromov-Witten theory of the fixed curve of symmetric product.
The proof of this, is that just like copy and paste of the previous proof?
Yeah.
Or is it?
Well, I mean,
or is it? Can you really put the two in the same kind of framework? Is it really some kind of statement?
Yeah. So there is actually many more ball crossings of this kind. Right. So it should be put in some greater kind of framework. Even though each of them, I mean, this, for example, case required, because it's not quasi-maps, you had to do some extra work to prove the properness of these master spaces and so on. Mm-hmm. For the quasi-maps, I just could say up to some details that this young Joe results apply. Here, I had to prove properness myself because it's not quasi-map, so it's different considerations.
So what would be the least common multiple of the two frameworks?
The least common multiple. What is that? Or what do you mean by?
What's the least common multiple?
Categorical sense.
Oh, I don't understand the joke. what is the?
No, I mean you have these two setups in which the stability conditions, more
Yeah.
or less the same, and the results more or less the same.
Yeah.
And so what do you think is the
So there exists. So essentially, it should be called something like wall crossing in Gromov-Witten theory. I mean, so there are many situations where you can exchange this behavior of producing a rational tail with the behavior of getting some kind of ramification.
Maybe you should think about it, sir. Maybe the way it's supposed to be thought about it, it's not really about any kind of target state. You just have some kind of what is it called, like a homological field theory of some kind.
I mean, it becomes complicated. Actually, the wall crossing on a cohomological field theory becomes complicated because of psi classes. Because in cohomological K theory, cohomological field theory, you always pull back psi classes from MGN, right? But here, the psi classes live on upstairs, and they are different from those that you pull back from MGN, and so it's. I mean, okay.
Upstairs where? In your covering curve?
In your, I mean, in the moduli space of maps, right? Or if you, I mean, there is some difference between the pullback and.
Well, anyway, it's kind of like you want it to be either mapped somewhere, or I would rather go for things which are, kind of integrate maps out, which is what with some kind of motion. So just something happens on the modular curve.
Sure, but then you have, well, I mean, but then you have, for example, to prove properness of each of the situation, right? I mean, it depends. What do you want exactly? You want a general framework to put the two situations on like the same footing or the same ground?
Sorry, I thought about this for like 1 minute, and you thought about this for a long time, so I don't want to suggest anything too profound. But all I'm saying, since here, in this situation, has to be anything at all. Right?
Yeah, here
so
actually.
you can map to any target you want.
Yeah.
So this means
Not just S.
No,
yes,
yeah.
right. So we don't know much about that. That could be anything at all.
Yeah.
And so if you have that sort of thing, I would rather make it a statement just about modular curves. You have some kind of collection of classes on two different classification modular curves.
Sure.
And you just compare them.
But this is I'm making a statement about not classes on a modular space of curves, but about numbers that you get from those classes.
Right, but you can push it. All this computation that live on modular curves, you can push it forward. And
So
some sort of comparison between different stabilities on.
So I mean, actually pushing forward to MGN is probably not a good idea, because you, again, because of way the psi classes behave. So I mean, I thought about it for some time about constructing like a cyclotheoretic version of this wall crossing, right? I haven't thought about deeply, and I probably also at that point I didn't know much about Gromov-Witten theory at all, and so to me it just seemed at that point that it becomes more complicated because of how the psi classes behave. But I also was just lazy to understand it well. Because what you do, I mean, you can contract, you contract stuff, right? When you push forward to MGN, you contract some rational bubbles, let's say. Those might have some psi classes, some markings. And then when you push everything down to MGN, you kind of contract lots of information in a. Well, for example, young Joe, he proved everything by not push forwarding to MGN, but push forwarding it to quasi-maps to PN. In JT case, it always exists, and it's good because you don't contract stuff in that situation. And then, so he has a cyclotheoretic version on which live on like stable maps to PN. But in this case, you don't have an. Yeah, okay. I mean, I don't know. Something like that. Some cyclotheoretic version should be possible. It's just that one has to think how to.
I'm not even asking for cyclotheoretic versions of numerical stuff. It's fine too, but it just seems like it seems like it'd be good to have both things be special cases of something, one common thing, which is maybe maybe it will not eliminate the proofs of properness and stuff, but it's.
You mean construct also? I mean, okay. You also mean probably constructing a universal theory of which. Like specializations of which give either of those, and so I mean, there is a point of view which is kind of a bit also not non-productive, is to view quasi-map theory as epsilon goes from 0 to infinity, and this theory to view as epsilon to be negative. And so you view it as a one. You view it as a epsilon, so you can view epsilon now not in R positive but in the whole R. And then you vary epsilon, and you go like in some sense from Hilbert schemes to symmetric product. That's what they do in. I mean, there is equivalent story in this Landau-Ginzburg models. So there is a equivalence of I mean, if you take a, let's say, quintic, right? There is Claviau threefold Landau-Ginzburg correspondence, which says that if you take Gromov-Witten theory of a polynomial that defines, sorry, if you take Gromov-Witten theory of zeros of a polynomial that defines quintic, it will be equivalent to taking Gromov-Witten theory of the Landau-Ginzburg that that polynomial defines. And this is done actually by you can do wall crossing as well on both sides, and this is proven in some sense doing this wall crossing and then doing there is also analytic continuation around the zero. So it's some kind of, I mean, it's reasonable to think about it this way. Okay, let me actually, yeah.
But all I'm saying is that you have some, you have some kind of bubble, and you have a measure of, you have some kind of way to integrate over it. When you collapse the bubble, there's something,
Yeah.
Something happens. It's like that if you're, for every bubble you're trying to decide whether it collapses or not. It's very, very insensitive to what is it, what actually, where does this bubble actually matter? You have to whatever. You have Ginzburg, you have to orbifold, you have to quasi-map.
Yeah, I mean that's what I wanted at some point, like to have a. I wanted to have some kind of unified theory for all of these kind of wall crossings. I mean, there are others as well, and I mean, it's a work in progress in some sense. Like, to what is a good language to put everything under the same umbrella. I just don't have an answer right now. I mean, it's a very reasonable question that you're asking, and it's very natural. Like, because it's actually, I mean, this is not far from being unique phenomena. I mean, there is this Landau-Ginzburg stuff. There is other wall crossings that are also works in progress. it's kind of. There are many things. Yeah.
This Landau-Ginzburg one, is that the equivalence? Or
yeah, Landau-Ginzburg. So.
is that actual assignment?
I will say some nonsense probably because I don't remember exactly. So Landau-Ginzburg is exactly the same. So it's. I mean, you have kind of a Claviau threefold here, and then here you have Landau-Ginzburg that defines. So this is zeros of some polynomial, and this is Landau-Ginzburg associated to that polynomial. And then, so when you wall cross, I mean, when you can vary stability on this side, you vary stability on this side. So varying stability on this side corresponds to quasi-map stability, kind of varying quasi-map stability. Varying stability on that side corresponds to this FG, what is it, RV theory, or what is it right there?
I think this is correct.
Yeah?
But yeah, fine, Charlie.
Yeah, exactly. So, actually, what time is it?
12.
Okay. Yeah, I mean.
You can continue until my battery runs out.
There is just one last thing I want to. I'm erasing all that. No, I wanted to say something about Krepan resolution conjecture, but
Sure.
I mean,
You introduced notation for it, but haven't used the notation. It's something called CRs. You haven't seen CRs.
Huh? Well, let me just draw it. I mean, I'll not I'm not. I mean, I also kind of tired myself, so it's. I probably won't confuse people if I start talking about it right now. So let me just draw it. So you essentially. I don't know if it's a good drawing. So this should. So this is supposed to be Kähler moduli space. And so this some cusp corresponding to Hilbert scheme of endpoints and to the symmetric product. Well, here, I mean, you have some kind of balls, right? And so what does the Kreppmann resolution conjecture says? Well, essentially, there exists supposed to exist some.
I thought symmetric product usually sits in like a smooth ball. Like a zero, some kind of zero size.
This is the stack, so it's the stack symmetric product.
We're looking for the Hilbert scheme. Let's look for the Hilbert scheme of point. That's really, it's kind of z equals 1.
Right, but it's on a wall.
Yeah, even for the Hilbert scheme, it's not even on a wall.
You mean had the size parameters?
The size parameter, size zero size. If you think of the symmetric product, it's really zero size.
Cycle goes to 0.
But anyway,
Yeah. So, well, yeah. And so essentially, what Kreppmann resolution conjecture says is that you take a. I mean, you take locally you have your Gromov-Witten potential defined, right? And then you can Kreppmann resolution conjecture says that you can extend it to some more into some neighborhood which also contains the point that corresponds to the symmetric product, and then essentially, well, if you have your correlation functions on Sn, if you now. So this is a Hilbert scheme. If you now substitute y equals -1, then this gives you the symmetric, the correlation function of the symmetric product. Okay.
So for SSA2, yeah. So it's a torus. It's just like a one-dimensional torus. Hilbert scheme is actually like a cusp as you've drawn, and then -1 is on the unit circle.
So, but you always can you actually produce orbifold seam, but not a coarse seam in this. I mean, you always produce coarse seam, right? You can you? When you're saying that seam is at the smooth point to like 1 on torus, you mean which seam?
Well, so
orbifold seam.
Coarse seam, I guess you want to think of as like not in the complexified Kähler modular space, but just like a different space where you only have like a real H2 or something. It's like an actual like Kähler class on the Hilbert scheme rather than complexified Kähler class.
Yeah, okay. I might ask you some questions afterwards about it, because I mean, drawing this Kähler modular space, I cannot say that I fully understand what's going on. So it's just I thought that it might be just useful for some people who understand it better. So, but what I want to say is that this Kreppmann resolution conjecture, well, it's proposed by Rouen, and then I mean in a cohomological setting, and then generalized in many other directions by other people. So you need just a specialization of your variable. Well, now I mean with these wall crossings, well, you can say that this now Kreppmann resolution conjecture of Cn and seam S is equal to the dt Gromov-Witten of the S times C. But in dt Gromov-Witten you have this change of variable So it's a y equals minus I u. While here in the Krepin resolution conjecture, you don't have a change of variable. It's just a specialization of the variable at some point. And what I want to say that this change of variable actually comes, so this change of variable comes just from the divisor, failure of divisor equation. Equation on a symmetric product. So what I mean by that is that you can, well, this Krepin resolution conjecture holds for any kind of any number of markings, and you can insert exceptional exceptional divisors on a Cn, which will not do anything because of divisor equation, so you can always get it out. But if you insert exceptional divisor in a sim S, what it does actually, it raises the number of simple ramifications. So you cannot really get it out. You actually get a generating series for this extended degree where you also take into account number of simple ramifications. And so here you obtain this exponential on the side of a Hilbert scheme of endpoints, while on this side you obtain just a generating series for M, for a number of simple ramifications. And so in the end, this specialization to -1 becomes this change of variable y goes to e minus e iu. Okay, so I guess it's good. Well, I'm sorry for going all the time so much.
Thanks for lectures. For lectures, thanks to all the work.
Well, I mean, I hope you learned something.